Yeah, you guessed it, part due. That is, we are going to use mathematical induction now to prove the sum of a series. Let's try our first one. So, in a perfect world, I'd have this on the board. I'd say, hey, Brooke and Ian and all you other cool people, go up there to the board and tell me what you think. What is the sum of the first, the second, and the third? So the sum of the first terms, the sum of the first two terms, and the sum of the first three terms. And you would suggest a formula for what you think if I had 10 terms or 500 terms or n terms. Well, when you do the sums, you get 1/2. 1/2 plus the second term is 1/6. Add those, you get 2/3. So 1/2, 2/3, 3/4, 4/5, and maybe, just maybe, you would come up with this crazy idea, as I get my pen ready, that S of n might be equal to n over n plus 1. No way. So like the sum of the first 158 terms would be 158 over 159. That's amazing. Huh, I wonder if it works. That's right. So that is our conjecture. Um, Induction means you look at patterns and you say, hey, I think this. That's a conjecture. All right, now to prove a conjecture is true for all n, maybe we have to plug in every single possible value, add them up, and see if it works. Woo, that's tough. All right, so there's a couple things in summation you need. You need your conjecture, what you think the sum is, but you also need a formula for the kth term, the individual kth term. So if we're looking at this, the first term is 1 times 2. The second term is 2 times 3. The third term is 3 times 4. So maybe the kth term would be k times k plus 1. And that is correct. All right, we need two things in order to prove this by mathematical induction, and that is the base case and the assumption of the kth. Does that mean the k plus first is also true? So in a base case, all you're doing is seeing, is your formula for your, does it work when I plug in a 1, in other words, the sum of the first term, does that actually equal the first term? So let's check it out. If we plug in a 1 into the sum formula, I get 1 over 1 plus 1. If I plug a 1 into the right-hand side, or the term, I get 1 over 1 times 1 plus 1. Notice the subtle differences. This is using the kth formula, and this is using our conjecture, the S sub n formula, n over n plus 1. And sure enough, you get 1/2 equals 1/2. The base case is true. All right, the second step is, I really didn't push that very, the second step is called the inductive step. So we assume p sub n is true for n equals k, or we could just say assume p sub k is true. Both work. So that's saying that if I plug in a 900, it's going to equal 900 over 901. Great. We're assuming that's true. I put this next to it because now is the kind of the idea of where do we want to get to? What would make our life really good? And that is, if I could somehow show that S sub k plus 1 is equal to k plus 1 over k plus 2. Notice I'm using our conjecture, and instead of k, I'm thinking about k plus 1. So I plugged in a k plus 1 here, and I plugged in a k plus 1 here. It's important to notice that I did a little bit of math there. K plus 1 is k plus 2. Now, this is what you want to get to. Okay, you can't start there, you can't assume it. All we can do is assume this is true right here. Okay, and with that, can we somehow get to this? Well, if we're looking at the terms, we have the first term, the second term, the third term, and so forth. Here's the kth term. Here's the k plus first term. How do I get those? I plug k into the formula, or I plug k plus 1 into the formula. I believe that should be a 1. That should be a Sorry about that. K plus 1 and a K plus 2. Okay, because the kth, yeah, that's right. Now, if I add up the first k terms, that's the sum of the first s sub k. If I add to it now the k plus first term, now I would have the sum of the first k plus 1 terms. You're like, really? You can tell me you add the next term? Yeah, I'm going to stop there. The idea here is it sets up an equation. If I take the sum of the first k terms, just notice I might be out of the picture. You know it's all about me. I don't know if that's better or worse, but all right. So that sets up the idea that if I take the sum of the first k, and this is what we assume to be true, we add to it the next term, and we know this. So we know whatever we get here is correct. We know that this is the sum of the first k plus 1 terms. We know it. Over on this side, it's kind of like, now let's use the formula. What if I plug k plus 1 into the summation formula? What do I get? And the key is that these two sides show. I will tell you right now, you don't write this. You don't write this right now. What you do is you assume that everybody knows what that is projected to be. And that's what's difficult about looking at solutions, is they never tell you what you're going for. You just end up here, and it's like you're supposed to have known that that's what you're supposed to get. So I'm just planting the seed. So how does this look? Well, I set this up, and I just figure out what it is. This is our assumed value that we assume is true. If we plug k plus 1 in, we get this. And now I just have to do some algebra. Common denominator. Okay, so I multiply top and bottom by k plus 2. Got this. All right. I can multiply the top out. I can factor. And since I have k plus 1 squared and over k plus 1, one of those cancels out, and I get k plus 1 over k plus 2. Is that what we're shooting for? Absolutely. So the world goes crazy, and we give it a bam skis. Pretty cool. Now, are we done? No, we are not done. I don't know if I wrote this on the next one. I'm going to check it out. No. So when you are finished, you need to take the time. This is a remark point, and you will get a point for that. Since P sub 1 is true, and that's just saying the base case is true, S sub 1 equals A sub 1, and P sub k implies P sub k plus 1, then the proposition P sub n is true for all n elements of positive integers. Now you're going to see some variations of this, but I addressed two things. I addressed that the base case, and I addressed that the assumption of the kth term implies the k plus first term. All right, so I'm going to try something I have never tried. This domino thing is, I think they're close, but I just want to be very clear about why you do these two things. All right, so the first thing you're supposed to show is that this is true. And in the sense of dominoes, means that's going to fall. That's going to fall, okay? Over here, we assumed the the S sub k is true, okay? And by using this and this k plus first term, we prove that our formula for S sub k plus 1 is also true. So now we know two things. We know we have a case, the base case, the first one. We know that's true. And we also know that somewhere, wherever we want, if we know this is true, it'll make the next one true. So check this out. I can choose where this is. Oh, don't want that to happen. Oh, I did. So does that mean I can go back? No. Okay, I think I fixed it. So where were we? We knew this one worked, and we know that if this one works, then the next one also works. So what we do is we just take this idea back to this, and all of a sudden, we know this is true, and we know if this is true, this one is true. Well, if that works, then we just now we know the second one's true. Well, if that's, we've already shown that if we know one is true, the next one has to be true. And boom, 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 they're all true. They're all true. Remarkable. I don't know if that helped. I'm just trying to help you with that domino effect. All right, this one just blew my mind. I love this one because it brings up what we just talked about. How do we know something is a factor? A factor. So use the principle of mathematical induction to prove that no matter what n I plug in here, x plus a will be a factor. Well, let's try the first case. Let's plug in 1 for n because this is positive z. Plug it in, we get x cubed plus a cubed. Maybe you're right at that stage where you can factor sum of cubes. It's always going to be equal to that. I'm so into division and synthetic division. What I did is I just said negative a into 1x cubed, 0x squared, 0x a cubed, and guess what? I got a 0. So both ways, the base case is true. Now we're going to assume that the kth setup is divisible by x plus a. Check this out. Wow. All right, assume. I plugged in k here. We're going to assume that is a factor of x plus a. Well, what does that mean? It's not like you can say 3m or it's not divisible by a number. But actually, yes, you can. If it's divisible by x plus a, isn't it just x plus a times something? Well, that something is not an integer, it's just a polynomial. Okay, and we know the degree of that is 2k because the degree of the whole thing is 2k plus 1. We know the degree of this is 1. Cool. All right. So just like before, we're probably going to substitute this in for something. Uh, when you plug in k, so now we're looking at the k plus first. So when we do that, we get something like this. I distribute the 2's. I'm getting nervous. I see that I can factor out an x squared here and an a squared here. If you're not, take a moment, prove to yourself that this is a true statement. I had to, but guess what? After I did it, I'm like, sweet. Uh, what did I do here? It looks like I added this term because I got x squared and a, and oh, look at this. I added this term and subtracted the same term. Can I do that? Yeah, but why? Well, the motivation here is, can I get this x 2k plus 1 and this a 2k plus 1? If I can substitute in this for it. So there is a motivating factor. All right, do you see that these both have x squareds in them? So now I can factor out that x squared from here and here. So I get this. This stays the same. I don't adjust this at all. This, I know, since I was so motivated, is equal to x plus a times p of x. I've got to use it somewhere. So I'm going to plug that in. Now I have this mess. Well, I know this is factorable by x plus a, but somehow I got to get an x plus a out of this. All right. Do you recognize I got a to the 2k plus 1 in both? So if I factor that out, but notice if I have a minus here, I got to kind of switch the signs here. So x squared minus a squared, remember I want x plus a, but this is where those who can factor are going to be loving life because we know that x squared minus a squared is equal to our good friend x plus a, x minus a. That is in this term, that's in this term. I can factor it out. It is now proven that the k plus first expression would also be factorable by x plus a. Wow. All right, more summation. Let's get back to summation. Sorry, that was just a fun one that they had, and I just wanted to do it. Okay, so we're going to prove that if I add up all the squares, I can use this formula. So if I wanted to add up the first 10 perfect squares, 1 squared, 2 squared, all the way up to 10 squared, I could just plug in 10 into this equation and I'd find the sum. I think. Let's prove that it works. Okay, so we got to do the first case or the base case. What are we going to do there? We're going to plug in a 1 here for n. So it's 1 squared, so 1. Plug in a 1 over here, and I better get a 1. Turns out I do. All right, so the first case is good. We're going to assume p sub n is true for n equals k. We're going to write this every single time we do this problem. And what does that mean? That means the sum of the first k is equal to k plus 1, 2k plus 1. Notice I have it right here. All right, at this stage, I always like to show what s sub k plus 1 looks like if I plug it into the formula. This is actually what we want to get to. We want to somehow start with this and end with this. All right, for summations, what you're going to do is add up the first k terms and then add the k plus first term. So when we plug that in, we get this. The k plus 1, 1th term is k plus 1 squared. How did I get that? Notice this right here will always be the formula for the general term. So if I want the k plus first term, I just plug in k plus 1 for I. So I get this, doesn't have a common denominator, so I multiply this by 6 and divide by 6. So now I have that. All right, so very important. Instead of multiplying this out and getting it a little bit crazy, it still works. Very important to notice that instead of expanding, I factor. Are there anything is the same in both? So yes, I have a k plus 1 and a k plus 1. So factor that out first. Then if you have to multiply because you got nothing else to do, multiply. All right, really important. I get some crazy stuff. I'm not too scared. I multiply it all out together. This would be a great time to take a peek at what you wanted to show. At what what you wanted to show. Oh, I can't erase that because it's already. So take a peek at what to show. So what I mean by that is this is what we wanted to get to. And look how close we are. We have the k, gosh, I'm not going to lose my temper. No way, no way. We have the k plus 1. We have the 6. And I wonder, it basically is telling you how to factor it. It said there was a k plus 2 and a 2k plus 3. So I wrote that, I multiplied it in my head. Yes, that is exactly how you factor it, and you are done. Every time for summations, every time. Maybe it's different on this time. Doubt it. Okay, let's try this one right here. If I add up perfect cubes. So the first case, the left-hand side, 1 cubed is 1. The right-hand side, I plug in a 1. I get 1 squared by 1. So I get a 1 in both. We're good to go. All right, we're going to assume the kth statement is true. What does that mean? The sum of the first k terms. The sum of the first k terms is going to be, and I look at this formula, k squared, k plus 1. Yep, very good. I like to do want to show what is the k plus first. What does the sum look like? I plug in a k plus 1 for everything, and I get this. So this is what I want to get to. All right, that's a nice thing to check out. So I just wish I knew why that jumps. All right, just slow down, move too fast. All right. So I take my assumption, I add the k plus first term. Remember the terms are all cubed, so I add this. Ooh, that looks kind of scary. If I had to multiply all this out, it'd take me a while, but careful, factor out before expanding. I say it again. It looks like I've got a k plus 1 squared in both, so that's what I'm going to factor out. Now I got some stuff, but at most it's going to be quadratic, so I multiply that out. and maybe I take a quick peek at what I want to show just to kind of give me some direction, and it says I'm missing a k plus 2 squared. Well, guess what? That just yeah, that's the same thing. Nice, everything works out. All right, so now we have proven by math induction that the proof of the perfect cubes are equal to that formula. You might be asked to do something. Well, add up all the perfect cubes, but maybe they start at 7 and go to 20. Well, darn it, our formula works from 1 up to n. So you have to look at it this way. Add them all up and then subtract off the first 6. Okay, so using the formula, 20 plus 1 squared, which is the k plus, or the n plus 1, n plus 2, and then I plug in the 6, and guess what? I get it correct because that is correct. I don't know what the number is, but it's a cool one. All right, we were at 20 minutes. I think we'll let you try this one. And I wanted to show you one with, it's just a little different. We show the first step is the first term equals the sum of the first term, and it works. Okay, our assumption that p sub k is true means that if I plug k in, I would get that for the sum. What do I want to show? I plug k plus 1 in. Do you notice how that k plus 1 minus 1 goes to k? K plus 1, good. So this is what I want to show. This is not part of the proof, but I think it helps kind of keep your mind focused on how you want to work it algebraically. So I add the same thing. This is the third or fourth time. I plug in to the correct formula. I plug into the correct formula. And then I've got some work to do. This 2k plus 1 minus 1 obviously is 2 to the k. I've got a 2 to the k here, so I'm going to factor out of this term and this term. This is just going to stay by itself on the outside. So I've got my 2 to the k, and it leaves me k minus 1, k plus 1. The ones are going to cancel out, so k plus k is 2k. 2 times 2 to the k is going to be, that's going to give me my 2 to the k plus 1. I got the k, I got the plus 1, I'm there. All right. Yes, I have one more example with factorial, but I think I'll leave that to the viewer to check out. There's our set of problems. Certainly worth the price of admission. We'll work on this until we get them. So if that's a day, great. If it's 2 days, soup, that's okay. 3 days, no, come on, we can do this. All right, good luck, everybody. Notice I have put all the solutions posted on these notes. Welcome to Proof by Mathematical Induction.